Alright, our next topic here is sequences. So a sequence is simply just a set of numbers defined by some equation. So we have, for instance, this first one, we have a sub n equals 4 plus negative 1 to the n power. So how we get terms of the sequence, so we get numbers. We go, so for example, we have a sub 1. So the first term is represented by that 1 as the n value. So we plug in 1 for n, and we calculate. So 4 plus negative 1 to the 1 power, that's going to be 3. And then we would go to the second term, a sub 2. Plug in 2. So 4 plus negative 1 squared would be 5. And we continue on. A sub 3, plug in 3, we end up getting 3. So this is how we think about it, but we write them out as a list of numbers. So we have 3, comma 5, comma 3. And if we kept going, 4, 5, we go even and odd powers, we know that that negative 1 is going to keep fluctuating between a negative 1 and a positive 1. So we just keep getting values of 3 and 5 back and forth. So that's that sequence. Another example, b sub n, we're doing the same exact thing. We're going to find the terms of the sequence, plug in 1, so we get 3 over 2. If we plug in 2, we get 6 over 3, which is 2. Plug in 3, we get 9 over 4. And so on and so forth. We just keep plugging values in to find the terms of the sequence. I think we get the idea here. There's a different type of sequence, so these are just standard sequences. This right here is a recursive sequence. So they give you some starting value. They give you your first term or some term. So they give us our a sub 1 value is 5. So what we do to find the next term, it gives us this statement. It says a sub k plus 1. So this is the next term. So this is the a sub k value. Okay. We plug it into here, and we get the next term. So our first term was given as 5. If we go ahead and we plug 5 into this equation, 3 times 5 plus 4 would be 19. And then we would take this 19 and we would plug it in for a sub k, because we're trying to find the next term. Okay? So that's all we do. So plugging in 19, we would end up with 57 plus 4. That'd be 61. Now we take 61, plug it in to find the next term. That's a recursive sequence. Alright, so they're pretty straightforward. We're just plugging values in to find other numbers. Now, the next thing we need to talk about is whether a sequence converges or diverges. So we're expanding on this idea that we've been talking about a little bit, about converging and diverging. So given a sequence, I want to know if I continue on putting numbers in this pattern, in this sequence, is it going to converge to a value, or does it diverge? So we have to continue on with this idea of taking a limit, just like we did with the integrals. So we're going to take the limit as n approaches infinity. I want to know when this number gets really, really big, what's happening to our values. So we go ahead and we take as n approaches infinity of our sequence there. So let's do that. Actually, you know what? We're going to start with the other one real quick. It's a little easier to see right off the bat. So this one over here, we just dealt with this one. This was the one that went between the values of 3 and 5. So it was bouncing back and forth between 3 and 5. So if we took the limit as n approaches infinity, we could do that. Or we could just think about that. If it goes to 3, 5, 3, 5, 3, 5, is it going to be converging to a value or diverging to a value? Well, this one is going to be divergent because it never settles to one value. So if we're alternating between two values, it's going to be divergent. Now if we take this limit, so if we think back to when we were talking about limits and we were doing L'Hopital's rule, this is a perfect example of that. So remember, we have to take this power down to the front, and the only way to do that is to use natural log. So we use natural log. So remember, at the end we have to use e. So whatever our answer is the power of e. So we're still doing a limit. And then we have to do the limit. So if we plugged in infinity here, we would have infinity times 0. We know that's an indeterminate. So we have to rearrange this a little bit. So that would be 1 over n. Now if we plug it in, we end up with 0 over 0. Still indeterminate, but we're in a fraction form now. Now we can run L'Hopital's rule. Now we can take derivative of the top and the bottom. Okay, so the bottom derivative would be negative 1 over n squared. Top derivative would be 1 over 1 plus 1 over n times the derivative of the inside. Derivative of the inside is going to be negative 1 over n squared. Okay. So pause, make sure you see how we got these values. So now we notice that we have a negative 1 over n squared on the top and the bottom, so we can just cancel these. Now we're just taking the limit of this. So if we do the limit as n approaches infinity, we end up with 1. So remember, I said, because we used ln, we had to do e. So 1 is a power of e. So we just have e as our answer. So if we get a value, if we get a finite value, we know that this converges. In this sequence, actually, the series, and we'll talk about series later, is where the value of e was created. So that's where this originated. All right, let's take a look at a couple more here, and then we'll be done. So do we have a situation where we converge or diverge? Well, I'm going to go ahead and start over here. Might be a little easier to see. So if we are trying to find if this converges or diverges, we have to run the limit as n approaches infinity. For this. So we can use our shortcut rule, or we can use L'Hopital's rule. So if we do L'Hopital's, we have derivative of the top, derivative of the bottom, because we would have infinity over infinity, so we can't use L'Hopital's. So we would end up with 1 on the top and -3 on the bottom. So we actually get a value, and we have to run the limit. So -1/3. Okay. Or you just remember your shortcut, you take the leading coefficient if you have the same power on the top and the bottom. So this converges. Same thing here, plug in infinity, we're running our limit. We have an infinity or infinity situation. So we can go ahead and take the limit. Of our rule here. So because we have infinity over infinity, we can go ahead and do L'Hopital's rule, or we know what function grows faster, top or bottom. So squared, and we have an exponential. We know that exponentials always grow faster, so the bottom's going to grow faster. So we know that this should end up being 0. But you can run through L'Hopital's rule too and get that value. So go ahead and do that on your own. Run through L'Hopital's, make sure you get the value of 0. So we have 0 here. And I can do that for you if you want in one of our meetings. But we have to remember how to do derivatives of exponential functions. So take some practice there, and let me know if you have any questions. So let's see here. Last topic, and I'm actually probably gonna do some examples in a separate video. So we have this idea of monotonic. Monotonic is a sequence whose terms get successfully larger or smaller. So for example, if we look at this picture, the first one here, the values are continually growing, they're increasing, so this is monotonic. Second picture, we get some fluctuation here. We're going between different values, up and down, so this is not monotonic. Okay. Third one, at the beginning we are increasing and then we go to decreasing, so this is not monotonic. Excuse me. Fourth picture, we are decreasing the whole way, so this is monotonic. The other idea here is this idea of being bounded or not bounded. So in the first one, we're growing but slowing down. So we're approaching some value here. So to be bounded, I have to have a value that I can't go past. And I have to have a value that I cannot go under. So we have a smallest value and a largest value. Same thing here in the second picture. This line represents the largest value that we attain, and this line would represent the lowest value. So we're bouncing between two values, but we're never getting bigger or smaller than this value here. So this is bounded. Both of these are bounded. In this second picture here, we're not bounded because this is going to grow. It's going to continuously go down unless there's an asymptote down here. In this particular picture, we're going to get into the negative numbers, and we're going to keep getting more and more negative. So this is not bounded. Same thing here. This is not. Well, this is bounded because this one has an asymptote. We're never going to get to negative numbers. We're going to get closer and closer to 0, but never touching it. And we have a highest value. So this is bounded. So I'm going to do a couple videos on, well, one video on a couple examples of if you're given a sequence, the actual rule of the sequence, how do we tell if it is bounded? Or how do we tell if it's monotonic? So I'll go over that.